making this video titled A Curious Pattern. And basically, it started when I introduced to an activity about the topic of combinations, but figuring out the lines of communication. For example, if you have 2 points, then you can only form one line. You can only one line between them, and if you have 3 points, then you can form three lines, and that would look like a triangle. And so, if you have now 4 points, then there will be 1, 2, 3, 4, 5, 6. You can form 6 lines. Obviously, this is an application of combinations. For example, when you draw a line, it doesn't really matter if you start from A to B or B to A. So it's the same way that when we name a line, it doesn't really matter if we name it A B or B A. So that is an application of combinations. And then one student pointed out a pattern. So from 1 you added 2 to get 3. From 3 you added 3 to get 6. And from 6 you added 4 to get 10. And it seems that the number that you add each time increases by 1, right? And so 6 taken 2 would be 15, I think. And then 7 taken 2 equal to 21. Because 10 plus 5 is 15. 15 plus 6 is 21. That was not really an obvious pattern. That was not very obvious. And the first thing that came to mind was, is this a general pattern or just a coincidence? And so it turns out that it is. It is a pattern when r equals 2. It's actually very obvious now. It's not obvious then, but it's obvious when we look at the Pascal's triangle. Look at Pascal's triangles actually. You can see that there's a pattern of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. To really explain what's going on, we have to go back to the ways that we can find combination values. So there are 3 ways as far as I know. First is the classic combination formula. Ways of choosing n things taken r at a time is n factorial all over r factorial and minus r factorial. The example for that is already been shown. So that's the formula that I used before. So another way of finding combination values is through permutations. For example, if you're looking for the number of ways of choosing 7 objects taken 3 at a time, then you can first look for the number of permutations of 7 objects taken 3 at a time divided by 3 factorial. Basically, for finding permutations, all we have to do is actually remember the fundamental principle of counting. So the number of permutations of 7 objects taken 3 at a time just be equal to 7 times 6 times 5, and divide by 3 factorial. So 7 choose 3 is equal to 7 times 6 times 5 over 6 is equal to 35. So that's how we find combination values using permutations. And the third way is a much quicker way, much faster way of finding combinations using the Pascal's triangle. So to generate the Pascal's triangle, first we write 1. Write 2 ones below it. So initial that's the initial steps. Okay. And then next is you add these 2 ones together to get 2, right? 1 plus 1 is equal to 2. And then after getting 2, again write 1 to the left, another one to the right. You again add 1 and 2 here. So 1 plus 2 is equal to 3, and 2 plus 1 is equal to 3. And again, add 1 to the left and 1 to the right. So that's basically how you generate all the other values of Pascal's triangle. And so, how can we use this to find combination values? First thing you do is you find n, right? And to find n, the first level of Pascal's triangle is n equals 0. Second level, n equals 1. Third level, n equals 2. Fourth, 3, and so on. So that's how we locate n. In locating r, go from left to right. So left to right. So for example, you want to find the value of the number of ways of selecting 6 objects taken 3 at a time. So again, you first locate n. So n is this level, n equals 6, right? N equals 6. This is n equals 6. And then from left to right, you start with 0, 1, 2, and then 3. So 6 choose 3 is equal to 20. And so that's how we find values, combination values, using the Pascal's triangle. And it's even faster than using the formulas, right? However, this is only limited for very small values of n, right? So say you already have an existing Pascal's triangle, then from n equals 0 to n equals 10. What does this have to do with the pattern that I described earlier? Then you can see then that for r equals 2, the values of r equals 2 are right here, right? Because you start with 0, 1, 2. So the values for r equals 2 are here, right here. These are the values of c and r from n equals 2 here to n equals 10. And so if you can recall how we constructed the Pascal's triangle, you notice that 3 is actually the sum of 2 and 1, right? 3 is the sum of 2 and 1 above it, the two numbers above it. So that's how Pascal's triangle is constructed. So you added 2 and 1 above. And so to get the next value for 4 choose 2, then you need to add 3 and 3, right? 3 and 3 to get 6. And then to get 5 choose 2, then you need to add 4 and 6 to get 10. To get 6 choose 2, then you need to add 5 and 10 above to get 15. And so it's very apparent now, it's very obvious now from the pattern that I described earlier is not a coincidence.